Alrighty. This is our Physics 211 project number 2. I'm Zach.
I'm Tobin.
And I'm Tristan.
We went ahead and chose problem number 2, the problem with the box and the springs. And then starting with what we know, we're going to explain how we solve this problem. So what we know is that the springs are identical and will react and interact the same way because they have the same spring constant as prescribed by the problem. We also know the surface is frictionless, meaning there is no need for us to calculate in a coefficient of friction and factor it in to our velocity and acceleration equations because nothing else will be slowing the blocks down besides the blocks themselves. We also know that the blocks start at a rest, meaning we will have to calculate our starting velocity and accelerations based off the compression of the first spring that's compressed by a distance xi. We also know the blocks are different masses, so they'll have to stay separate throughout the entire equations and cannot be combined to make a simpler equation. Per the problem, the boxes stick together when they collide, pointing towards a perfectly inelastic equation that will conserve momentum, but we'll get more into that in our assumptions. And we're trying to find how much the second spring is compressed by a measure of xf or x final for how much that spring is going to be compressed. And the final bit of information we know is that the first spring is compressed by a distance of xi or x initial. Going into our assumptions, we're assuming that the springs are ideal, meaning they are massless and have the same, are uniformly tense throughout the entire spring and don't react differently based on different compression, and they perfectly follow Hooke's law and are constant in their movements. We're also assuming the collision is perfectly inelastic due to the blocks sticking together, meaning momentum is conserved and we won't have to calculate out any loss of force or energy in the equation. We also know we're also assuming there's no deformation of either springs or boxes in the system, meaning we don't have to calculate any loss of momentum to changing shapes or bending of items. We're also assuming it is a closed system, meaning that only the forces from the springs and the boxes are going to be taken into account and no other outside forces are acting on the system. And then finally, our coordinate system is just a number line starting at x initial and moving to the right in the positive direction, allowing us to have nice clean numbers to do our calculations with. Concepts we used to solve this problem was the conservation of momentum, inelastic collisions, and Hooke's law. Starting with inelastic collisions, this is just a formula to show that in inelastic collisions, everything is conserved and that it just rearranges the equation for two systems now working in one equation. The formula for Hooke's law just shows a perfectly ideal spring with no other outside force depending on its spring force, where it's just the spring constant and how much it's being stretched or compressed. And for the conservation of momentum, it's just an equation showing two different momentums moving and then becoming the same momentum with no loss because it is conserved. And then with these assumptions and what we know, I'm going to pass it over to Tristan, who's going to give us our solution.
So now for when we're solving the problem, we're going to start with some known quantities, starting with the mass of block B, which is in kilograms, as well as the mass of block R, which is also in kilograms. We also have that negative xi is the compression of the spring on the left, which is in meters, and that the initial velocity of block B is 0 meters because it's at rest. So our equations we used here are the kinetic energy equations, the spring potential energy equation, and some theorems of the conservation of momentum, as well as the conservation of energy theorems. For finding the solution to this problem, we broke it down into 3 parts. The initial situation where both blocks are at rest, during the collision, and the final situation when the spring is compressed. Initially, we're only looking at the left spring and box B, so we use the conservation of energy theorem and use the equations of kinetic energy and spring potential energy. This allowed us to solve for the velocity of box B just before the collision. The final potential energy, which is just before the collision, and the initial kinetic energy are both 0 in this situation, which makes it easier to solve for our velocity. When the two boxes collide, We're told that they stick together, which tells us that this is a perfectly inelastic collision. This means that momentum is conserved. We use the equation momentum equals mass times velocity and the inelastic collision formula to give us the velocity of the two boxes as they move towards the spring to the right. We can plug in the velocity we got in the last step and set the initial momentum of block R to 0, since it starts with no velocity. From here, we can solve for V, which is the velocity as both the blocks move together towards the spring on the right. Next, we will solve for the distance that the spring is compressed, which is what we are solving this problem for. We can plug in our values to find the initial kinetic energy of the two blocks, which is equal to the final potential energy, which has x displacement final as a variable, which allows us to solve for x final. At the end, there's no kinetic energy, and there's initially no potential energy, so we can set each of these to 0. From here, we can plug in our values, which we have found in our previous steps, to solve for the final displacement in x, which we have here.
Okay, just to make sense of our answer and let us know that all our steps we took were correct, we did a quick unit check. So we see that our final output is going to be in meters, and under the square root, we have kilograms times meters squared over kilograms plus kilograms, which can be simplified below. And then the kilograms will divide each other out. So that's left with the square root of meters squares, which is just meters. So we get meters equals meters, which shows that our units check out. And we also did a sample calculation just to make sure everything made sense in that realm as well. So with the initial displacement of the first spring of negative 0.5 meters and a mass of the blue block of 1 kilogram and the mass of the red block at 2 kilograms, the final displacement of the second spring was found to be 0.29 meters roughly. And all these answers made sense, so we felt that our final solution was correct. So to make sense of it all and wonder how this applies to real world situations and just changing the variables, how that would affect the answer. So the first question we thought of was, how would changing the mass of one block change the x of f, the final displacement of the second spring? So we found that increasing the blue box's mass would always increase the displacement of the second spring. If we make it lighter, then the distance will be less. And the inverse was true of the red box, which, remember, the blue blocks would have to make go from 0 meters per second to whatever the final velocity would be. So the greater the red box was, the less the spring would compress. And then changing x of I, impacting x of f. So obviously with a smaller initial displacement, the final displacement will also be smaller because you have less force pushing the blocks. So these were positive and negative for this instance. And then we thought about if the surface had friction, if it wasn't ideal and there was some sort of force on the blocks that we had not accounted for. So if there was friction, we had the possibility of the blocks not reaching the spring, and for any amount of friction, the x of f would be less than it was if there was no friction. And we also wondered if the collision was going to be elastic, how that would impact the final distance. And we found that if the collision was elastic, we would only have one block going towards the second spring, which would decrease our x of f since there's less mass.
And then coming into our reflection, we found this problem was similar to a class problem we did with a belt with a box held to a spring under load, and then calculating the velocity of that block when released. We felt it was very similar to the first section of the problem and was helpful in those calculations along with the second. And then in a get ready activity and a couple lectures, we went over inelastic collisions and how they affected momentum. And particularly with inelastic collisions, how they conserve momentum in the collision, and how pieces stuck together, especially with perfectly elastic collisions like we assumed. But in order to solve this problem, we had to kind of piece a couple problems together and their problem-solving activities in order to solve it fully. The conclusion was, using these concepts, especially conservation of momentum and Hooke's law, we were able to solve this problem. And finding in our making sense, we were able to find that when you increase the initial distance that the first spring is compressed, the further spring will also be compressed further, vice versa with the blocks interacting the same way. But then that is our solution, and thank you very much.